All right, so today we'll take our second stab at differential equations. Nice, pretty easy introduction on Monday with initial value problems. And the kind of initial value problems we gave you were of an easier kind than we've been doing. So we'll encounter some more initial value problems today too, but with differential equations that are harder. Even on Monday, I gave you a differential equation. I just put one out that was harder. That I said immediately, like, here's a differential equation. Its solution is some function. You can check that it works, but you don't know how to get it. So today I'll throw a differential equation at you that's just like a little bit harder, right? Notice right away why it seems harder. Can you verify just in your own mind that this is harder? Okay, good. I mean, what makes it hard? Well, I don't know. There's a y, you might say. In fact, my first thought about this might be, this looks a little bit, somewhat, familiar. The kind of derivative that I'm getting today looks like the kind of derivative, the answer that you would have gotten from a problem earlier in this or in the first semester. Remember when were we doing derivatives? We got a final answer, and the answer was like dy dx equals some expression involving both x's and y's. When did that happen? Do you remember? Yeah, so this is kind of us unpacking some of that. Could you go backwards? If I showed you, after having done those implicit derivatives first semester, if I showed you the answer to one of the problems you gave, and I said, could you recover the original problem, please? That would be akin to what we're doing today, right? So that's what you have here. So I'll kind of talk through this first one slowly, and then we'll do some more as practice, of course. So first of all, we're going to recognize this as being a separable differential equation, and that's a new word for us. But a separable differential equation is one where you can do the following, and that is to separate the parts that have an x and the parts that have a y. And now if we integrate both sides with respect to x, notice now there's a little bit of hand waving here perhaps, but notice what happens over here. Over here we get an integral that makes complete sense to us. Just love this. Over here this is a little weird to talk about though on the left side. Well, what do you suppose happens as we do this? As we add things up on the left with respect to x? Is there an algebraic manipulation that you might suggest for simplify what appears on the left side? What are we really looking at? The integral of y to the negative 1/2 dy, right? Is that a fair way to say it? One might be tempted to write this too, and I think this is often how I write these too. Right away, I rewrite this original problem as y to the negative 1/2 dy equals x squared dx is kind of how I write it, and then I throw integrals on them. But like really technically, I think the way we've just said it is technically you can't like integrate one side with respect to x and one side with respect to y, but just know that that's not what we're doing. We're integrating both sides with respect to x. It's just over here it goes away. And so in the end you have this, but conceptually you can kind of think, okay, can I get stuff that has a y with the dy, and can I get stuff with the x with the dx? And the answer is yeah. If we can do that, what you've got is a separable differential equation. And of course, in some ways, I think that was the big jump here. That's the big leap. Because I think it's very clear now what to do on the left side and what to do on the right side. Right? You have two integrals to solve. Just do them. What's the antiderivative of y to the negative 1/2 with respect to y? Well, of course, it's y to the 1/2 times, what do we need there? Yeah, times the 2. And then on the left, or on the right, we have 1/3 x cubed. And of course, don't forget the constant of integration. Right? Now, why do you only need one? You might object. You might say, don't we need like a c on both sides, or a c1 and a c2 or something like that? And the answer is like, sure, if you would like that, you may. But of course, as soon as you write 2y to the 1/2, if this is your work, say, plus c1 equals 1/3 x cubed plus c2, well, notice that these are just constants, and so my C is just your C2 minus C1. So let's just call that one constant. Is that fair to say? So some of you might be confused by like, what happened to the constant on the left? The answer is, calm down, it's okay. We're taking care of that. One constant is all we need to do. I guess we answered that. And then applying the initial condition, even in this form right here, is a fine place to do it. If you plug in 0 for x and 0 for y, apparently, nice, easy for this first problem, nice, easy initial conditions, then it's clear that C needs to be 0. And so our final solution is this, just without this, plus 0. Of course, if you would like, and I think we might like, you might like to solve for y. Though I will say, on many of these, it will be either very difficult or impossible to solve for y. And so the final answer may be some equation that isn't solved for y. Sometimes it will be requested of you to do that, and so you should. Sometimes it won't, and so you don't have to. Right? Again, this makes sense, because what kind of problems did we say we were kind of undoing here today? We said these are kind of akin to us undoing the what first semester problem? Not quotient rules, but say it again. Yeah, implicit differentiation. What kinds of things were we implicitly differentiating? Oh yeah, equations that weren't solved for y. So it makes sense that your answer could. Now in this case we have it solved for y, yay. But in general your answer might be, something that sine x plus sine y equals 2x or something like that. Well, whatever. It could be something crazy. All right, so let's take this really looks like the kind of thing that we got from implicit differentiation, doesn't it? As an answer first semester. So let's practice again here. Is this, first of all, let's confirm that this is separable. The question claims that it is in the asking, but let's just confirm that we agree with that too. It's very easy to separate this one. You just need to do what on both sides? Multiply by 3 minus y squared. Oh, I need to cut it. So go ahead and do that. So get 3 minus y squared times dy dx, if you want to kind of slowly go through this, equals 2x plus 1. And then integrating both sides with respect to x, we're going to have an integral over here with respect to y. Oops. And an integral over here with respect to x. All right, well, see if you can finish. I'll give you a second to do the rest of the work there. Apply the initial conditions too. Remember, we're solving an IVP here, right? Don't leave me with a C. plugging 0 in. We can do it right now here. Plugging 1 in for y, or plugging 0 in for y gives 0 over here. And 1 plus 1 plus c. Did you get c is negative 2? All right, so, and again, we can just write this as our answer. 3y minus 1/3 y cubed equals x squared plus x minus 2. So notice on this one that it's not only like hard, it's perhaps for us like really in some ways it's really impossible to solve for y here, even if you wanted to. So it's still worth asking, just like we did first semester. I think that we showed you a bunch of pictures of these implicit curves just to kind of like, not that we would expect you to know what the graph of this looks like, but right away this tells me this is an interesting kind of equation. It's not a conic because we have a y cubed in there. Anytime you have an equation that has x's and y's with powers as great as 2, with one of them raised to a cube to the third power, you get something very special called an elliptic curve. And elliptic curves look like this. So this is this equation right here. And so elliptic curves, well, they come in different forms. They can come like this, or they can come, there's sometimes a spot here and then like that going the other way if the x is cubed, or sometimes they're connected. They have, this actually doesn't have two sections, it actually connects like that. So yeah, you begin to recognize this coming up a lot. It's a very important kind of curve for cryptography. Most modern cryptography is based on this kind of a function called an elliptic curve. And a bunch of abstract algebra. More later, if you want to come chat with me about elliptic curve cryptography, you can. All right, let's do another one. Again, this time I'll leave even the work of separation to you. You'll see right away that this looks messy, but then almost immediately when you separate, you're like, oh, I see what you did. This is actually really nice. So less hand-holding here. See if you can do the whole thing. And notice there's no initial condition. That's fine. You'll have a general solution with a C in it. That's fine. When you're done, just check with your neighbor that you have what they got. Yeah, here's another one that I think is not really good to be trying to solve for y on this one probably either. Yeah, so you like that left side and the function involving y actually turns out to be nice, right? This happens pretty quickly, right? So you get 1 over cosine squared y integral dy equals the integral of 2x dx when we separate. Well, of course, this is just what, which is nice. Yeah, it's the derivative of and over here, 2x, that was us doing you a favor too. Things come out very nicely here, don't they? So if you were to solve for y here, it would be a little messy. You'd have to say y equals the inverse tangent of this, and then you'd also have to say like kind of plus pi n or something, because technically there are infinite numbers. You know what I mean? Like, yeah, let's just not have the discussion. Here's the graph of that implicit curve. Yeah. By the way, you can graph these too online. You can go to Desmos. If you type this in Desmos, you guys like Desmos, right? You can type this right into Desmos and it'll graph it for you. Just great. Tan y equals x squared plus c. And you might ask, mathematicians, do they have like an intuition about what this will look like? The answer is not really, no. No, I didn't expect that picture either when I typed it in. I was like, oh, that's cool. That's cool. I mean, you do get a sense that there will be some kind of periodicness to this because it's a tangent function. So you have obviously repetition every pi n. In fact, I think I'm going to guess that these are exactly pi units apart vertically. Yeah. Anyway, general solution is all we need. There's no initial condition, so we'll box that answer and be done with it. Let's do another one. This one, let's notice this time it's asking us to report the solution as a function of f of x. So please obey that constraint. Is it obvious that this is separable on the front? I mean, we tried to make it look not separable a little bit. Ooh, can you handle an xy squared? Well, yeah, I think we can separate that. What will we do first there? Well, we can race through the details of this. I mean, really, the end of this problem is the interesting part to me. So we'll kind of race through the front details of this problem. So that's x squared, y squared, of course. So we'll be integrating y to the negative 2 dy equals the integral of x squared dx. So far, so good. Over here, we'll get negative y to the negative first. And over here, 1/3 x cubed. And plus c. So no huge surprises yet. Let's put in 1 and 1. So it looks like c is negative 4/3. So going back here, I mean, I might write this, but now the calculus is not the issue. How do we solve that for y? Let's be very careful in doing it. I think we can handle it, though. I think I left myself room. So, what do you get there? Y equals, let's write this as a function of x. What do you have? Oh, go ahead.
So, can you like solve for it and just use c like as a number, so like negative x plus c over 3? It'll be like different for the negative and the c.
I mean, I think you're suggesting that we write the solution as like negative y, negative first equals 1/3 x cubed plus. Well, yeah, absolutely. Do you want to simplify and then use a substitution? Yeah, absolutely. This substitution can happen here or after, or either way. Yeah, good question. Absolutely. All right, so what do we get there? 1 over, how do you want to write this? 4/3 minus 1/3 x cubed, maybe? Or, I don't know, maybe you have a desire to multiply by 3 everywhere? Something like that. How do you like that as a solution? Sure. That looks nice. Okay. Now, the only other part that I think that's satisfactory, and I just want to say right now that is about all that AP or we will ever ask you in a testing environment, but I do want to have this other extra little discussion with you, and that's this. And state the domain over which this is valid. So I'm going to give you a very, very simple differential equation that we can solve visually, and I want to illustrate this point here. If you were to solve this differential equation, this graph looks like this, and we did this I think earlier in the year. This is the graph of, it's called the signum function. And what would the antiderivative of this be? It's not obvious from this form what the antiderivative of that is, but from this form maybe it is. This is +1, this is -1. So what graph do you know of that has a constant slope of 1 on the right and a constant slope of -1 on the left? What? Close. Yeah, absolute value function, right? We need y equals x on the right. You're right. On the right side, we need y equals x, but on the left side, we need like y equals -x or something. So yeah, but I don't know if you remember this discussion. Certainly, y equals the absolute value of x works, but talk to me here. What else works? You remember this discussion? At least in my class, I had a little bit of a discussion about this picture. What else has this as its derivative besides this picture? Yeah, you could of course add a constant, but it's worse than that. right? You get certainly the absolute value of x plus 17 works also. It's worse than that though. Not quite. Yeah. No, then you'll get like a slope of something different than 1 and negative 1. There's something that the discontinuity in the derivative allows us to do this kind of crazy with this graph and still have it be.
Have like 2 separate lines that don't actually meet up.
Yeah, so the picture could be like this, right? Doesn't that have as its derivative? That picture there, doesn't that have this as its derivative? Yeah, it definitely does. Including at the origin, is the derivative undefined here? Yes. Perfect, that's what we wanted. So it actually perfectly satisfies this differential equation. So if someone gave you this picture and said, find me, that is solve the differential equation, find me the function that does this, and say they even specified an initial condition, and I need this to go through the point 1, 1. Well, notice that, that this function would work, right? This would go through, this side would go through 1, 1. But what you couldn't nail down, if you gave me an initial condition on the right, what you couldn't nail down is the part on the left, right? And so if you were solving this little cute differential equation off to the side here, you would have to specify the domain of validity to be only, I know that the solution is y equals x, or the y, if you want to say y equals absolute value of x, that's fine. But only for values that are positive, right? So we need to kind of, we could, if we want to be utterly technical, we need to do the same kind of thing here. It's maybe not obvious that that's true here, but is there a discontinuity in this graph here? Where is the discontinuity? It's not nice. What is it? Yeah, cube root of 4, and that's the only real value that makes the denominator 0. There are 2 other non-real values that make the denominator 0, but we won't worry about those. Yeah, so the cube root of 4. So now we need to think, are we to the left, at this initial condition, x equals 1, are we to the left or to the right of that value? We need to kind of think about. Yeah, we're to the, well, if x is 1, the cube root of 4 is greater than that. So I think we're on the interval to the,
Why is it greater?
I mean, I'm just saying the cube root of 4 is something bigger than 1. You convince yourself of that. All right, we can talk more about it, but yeah, so I think that the domain of interest here for us would be from negative infinity to the cube root of 4 is like where this solution is actually valid. Again, this is a complicated enough discussion that like usually it's reserved in more full detail to a differential equations course. But I just wanted to like give you the honest truth right now that like we can't just like box this without saying, putting that footnote on this. Like technically, this is the domain of validity. And I have a picture for you of this function. Here's the function that we just got. So like we just said, the only domain of validity, here's the initial condition, 1, 1, and this is what this function looks like. It's only valid technically from negative infinity to the cube root of 4, which is where this vertical asymptote would be if we marked it. And so what about this side? Well, we really can't technically nail that down for exactly the same reason that we couldn't nail down the other side of the absolute value function, right? We're not, you know, it wouldn't be wrong to say this. It would just not be like, it would be you expressing more confidence in your answer than you should, right? It doesn't have to be there. This definitely, we're very confident about the heavy blue line there. That's definitely what that side of the function has to be. Here it is with subject to a different, same differential equation. Just want to show you the picture. Here's the solution if you use this initial condition. And notice that you're nailing down a different part of the function then maybe, right? So it depends on where the initial condition is given. Again, a discussion that if that went over your head, it's actually fine. Because, like I said, no one will actually ask you that for the domain of validity in this course. Again, we just wanted to like say there is more to talk about. Okay, now that we've said it, we don't really need to have too many more conversations about it, but I think it is worth mentioning. This looks fun. Look at that. We got a y, cosine x up in that exponent. Edge the board. Take a few minutes to do that. Okay. This time the front of the problem is actually a little bit interesting. And compare with your neighbors. Give you 3 minutes or so. I'm going to write an algebra 1 property on the board just to remind people of it. There you go. In case you didn't remember that property. It's in red with smile. What integration technique are people using out there? Other ends up being a U-Substitution one. That sounds like a good fun time. There's some work to do on the back of this problem too in terms of solving for y. I think that's going to be interesting. But everyone at least is at the place where they've gotten an implicit thing with x and y that satisfies the differential equation. Satisfies the initial conditions. Notice that by separable, we really mean like kind of multiplicatively separable, right? You might be tempted to think that something as simple as this. Check out this very simple differential equation over here that you can't solve, right? This is not separable. As simple as this is a differential equation that we will not solve in this course. X times y, wonderful. X plus y, we don't know how to do. Okay, so just keep in mind that that's not technically separable. If you try, just go ahead and try to. It doesn't. You can't write it in this form where you have the integral of some function of y times dy equals the integral of some function of x times dx. You can't get this in that form. All right, so over here we get what? Negative e to the negative y. And over here, oops, sorry, missed a. And over here we can probably, this U-substitution over here is not too bad. We can maybe just do it in our head, right? I mean, the thing that we expect to have happen happens, right? It's going to be e to the cosine x. All right, well, the derivative of the cosine is going to be negative sine x, so that's going to pop out. So if we have a negative waiting for it, I think that the derivative will be this. Is that your thought too on this? Plus a constant. Do you want to apply the initial condition now or after we solve for y? We'll take kind of, you want to take Moon's approach or our approach? Huh? Solve for y first? Sure, let's go ahead and do it. So e to the negative y equals, let's just get rid of that. Is it okay if I just make that, I decided to make that a negative. This c is actually the opposite of that c, but let's still a constant. In fact, we can play even play looser with the constant a little bit, and we will in a second. So what's negative y? People who know their pre-calculus. How do we recover this from an exponential function here? Yeah, we need the natural log of e to the cosine x plus c. And so we're close here. I'd like to go a little further than this. And I'll show you how we might do that now. At this point, you can apply the initial condition if you like. Yeah, I meant to do that otherwise. Yeah, so there's one other thing that we can do that makes this solution come out very, very nicely. Well, not very nicely, but better than this, I think. I'm going to suggest that we write instead of, yeah, you could put a minus c if you like. My c changed to a, it doesn't matter, so it'll be a different c, but yeah, I guess actually maybe that is the best way to write. I'm trying to think if there's another way to recover. I'd love to be able to like apply. No, I think that's a good place to leave it. Maybe. Okay, so we'll leave it there. I thought maybe we could take it further. But. Okay, and then you applied the initial condition to get. Let's see if we can just pop this in here. Pi over 2 is 0. E to the 0 is 1. What do you get there? See, in some sense, I might have rather have substituted it here, right? This is fine, but now I have to do this again, basically, to figure out what c is. So we get e to the first, if we kill the negatives, is equal to 1 plus c. So c is equal to e minus 1. Got under control. Alright, so does that work? You can check many of these today too. I want to remind you, you can go back and check these against the original solution too. So, I don't know, it's easy to have made a sign error somewhere. Do you agree with what we see there, Jackson?
Yeah, I'm confused what happens to the negative. When you have negative e to the negative y equals negative e to the
Okay, this seems to be tripping people up. Let's go back and do it all. I promise the solution.
Pardon the interruption, Richard Montgomery High School. This message is for Richard Montgomery host students and our Chinese guests. This is just a reminder that the Chinese students should arrive to the main office after the third period. Again, Chinese students should arrive to the main office after the third period. Thank you.
All right, the solution is still what I have in the box, but do you agree?
Okay, yeah.
So,
Yeah.
I just decided, like I said, we can play a little fast and loose with the constant because, like, say you multiply your whole equation by 2. Do you need to update your constant to be like 2c? Well, not really. It's still a constant. So, like, when you go to solve for it, you'll get something, some constant, you know? So you can be okay with that, yeah.
Is it possible to like put the c outside that line?
Not really, and that's what I was thinking that too. Actually, is what I was thinking. And then I was like, oh, actually, there isn't a nice way to simplify this. Yeah. I think maybe you're thinking of like if you have e to the cosine x times c, then you can like use that log property to separate it out or something. But yeah, there's not another. I don't think there's another nice way to write that. It does say asks for again the domain of validity. I think in this case it's actually somewhat complicated. I think I have a. I wrote it down somewhere, but it's not nice. It'd be when. Let's see. Does that always end up being positive in there? Certainly the natural log function would be undefined if this was ever negative. But can you convince yourself that that's definitely never negative in the parentheses? This is at most e to the 1, and this is at very least e to the negative 1. this thing here, right? Which is 1 over e. And e minus 1 is certainly positive. So won't this always be something positive? I think the domain of validity here will be all reals. So I'd like to maybe think about it a little more. Yeah. One over inside here. Yeah, if you're great to write the solution this way if you want to. Yeah. Is that what you want to do? No. This is what I mean. Try it here. If you plug in pi over 2 to mine, do you get -1? Let's do it. Cosine of pi over 2.
I brought your stuff.
Well, try it in yours. If you plug pi over 2 in, do you get -1? Try it. If you do, that's good. If you don't, that's not good. I'll take a look. All right, theoretically, we have someone else.
It was like 1 week late. And I said it paid back. And I said when I paid back. What way is it on her? I paid it back whenever I was the first time when I popped out during lunch.
Yeah, but then you sent the picture.
I mean, do you want to come down to Richmond and get it? If you wanted to, I would have been fine with that. There's some people who are going to be out on Friday, I know, 4 of you or something. Come take the test with lunch.